First, we look at circular locus, where we're given a locus, and for our chosen values, we pick 6 for A, 7 for B, and 5 for R. And we substitute in the formula to get this equation. And then, to find the Cartesian form, we will first let Z equals to X plus YI. We substitute into the equation and we combine like terms. Then we open up the modulus to get this equation. And this equation shows that the midpoint is 6, 7, and has a radius of 5. To find the modulus of extrema, we first have to define a line from the origin to 7, 6, 7, where we get y equals to 7 over 6x. And we substitute into the circle equation to get the point of intersection. And then our x values, we get this. Next, using the values we got from last part, we will substitute into the formula of z, by x equals x plus yi. And to find the z max, we use the plus. To find the z min, we use minus. And we get the values of z max and z min. And for general proof of z, the magnitude of 0 is equal to root 55. And when we put it in the formula for general proof, we get the same values as the one we have calculated.
Next, we will talking about optimization circular locus. And we will use the data, and the data is given, which is z origin equals to 6 plus 7i and radius equals to 5. Next, we need to define the minimum argument z and maximum argument z first. And we know that argument z equals to arctangent y divided by x. And the minimum argument z is the smallest angle between the positive x-axis and the line joining the origin to a point on the circle. And maximum argument z is the largest such as angle. Next, we need to substitute a line y equals to mx into the circle equation. So first, we need to let a line from the origin be y equals to mx. Then substitute into the circle equation, then expand and simplify it, the relationship of y equals to mx with the circle. The equation becomes a quadratic in x. So if there are two solutions, that means the line intersects the circle, and if there is one solution, that means the line is tangent to the circle, and if there is no solution, that means the line does not meet the circle. So we can know that the extrema of argument z occurs when the line is tangent to the circle. And then we need to set the discriminant to 0 so that we can get the final answer of m, which is 7.34 and 0.3. And then it can be written as z equals to x plus yi, so that we can get the larger slope m equals to 7.34 corresponds to the maximum argument z, and the smaller slope m equals to 0.3 correspond to minimum argument z.
Next, for the proving of z minimum and z maximum for circular locus by using GeoGebra, first we need to construct our locus on GeoGebra. Then, by using the sweeping circle method, we construct a circle at the center 0, 0. After that, we increase the radius of the circle until the circle intersects with our locus. The intersection point is the z minimum, and if we increase more of the radius until the circle covers all the locus, the intersection point is the z maximum. Then, for the proven of minimum and maximum argument z, first, we draw a linear line with gradient that our friend calculated before, which is 7.339. The angle from positive x-axis to the line is the maximum argument z, and for minimum argument z, we draw a line with gradient 0.297. The angle from positive x-axis to the line is the minimum argument z.
Next, we will attempt to understand the elliptical locus. This is our locus, and it will only form an ellipse under the condition that the value of A is greater than the distance between the two foci. For simplicity's sake, these are the values that we will choose, making the distance between the 2 points 8 units in magnitude, and making the points aligned along the horizontal axis. Since the value of A must be greater than this distance, we will set it to 10. These values trace out this ellipse. Now, a defining property of this ellipse is the equation d1 plus d2 equals 10, which states that for any point along the curve, say point P, the sum of its distances to the two foci will always be 10. Now, using the Euclidean distance formula, we can express this equation in terms of x and y. This expression can be then simplified even further. To do so, we must utilize the isolate and square method, and we must repeat the process twice, since having done it only once, our result will still contain a square root.
Next, we need to substitute y equals to mx into the general equation. Then we should expand all the squares in the equation until we get a quadratic equation. Then we should set the discriminant of the equation to 0 to find the value of m. And then we will get two values of m, where we need to insert it into an inverse tangent to find the value of minimum and maximum argument. To find the action values of z modulus, we must locate the location where the ellipse is tangent to a circle centered at the origin. We use implicit differentiation for both the distance formula and the ellipse equation, and then we equate their derivatives to find the points of contact. Taking y back into the ellipse equation, we can solve the resulting polynomial to find the real roots of x, which pinpoints the coordinate for the z maximum and z minimum.
For the proven of z minimum and z maximum for elliptical locus by using GeoGebra, first we need to construct our locus on GeoGebra. Then, by using the sweeping circle method, we construct a circle at center 0, 0. After that, we increase the radius of circle until the circle intersects with our locus. The intersection point is z minimum, and if we increase more of the radius until the circle cover all the locus, the intersection point is the z maximum. Then, for the proven of minimum and maximum argument z, first we draw a linear line with gradient that our friend calculated before, which is 0.97. The angle from positive x-axis to the line is the maximum argument z, and for minimum argument z, we draw a line with gradient 0.096. The angle from positive x-axis to the line is the minimum argument z.